All right. Hello and welcome. I'm Jacob Henschen. I'm a teaching assistant professor at a R1 institution. So I'm kind of in this weird in-between space where all of my colleagues are pushing the research as hard as possible, and then I come in and I'm saying, hey, let's talk about teaching. So through this experience of working with the more research-focused faculty, I started to realize there were some common deficiencies in some of our undergraduates that we were taking up into the graduate ranks. And so that kind of led to me rethinking how I run certain class projects. And so that's what I'm going to be talking about today. So first I kind of want to talk about, okay, there's a clear motivation for us to involve undergraduates in research and real research. And the previous speakers did a really nice job of showing you some good examples of that. And I'm going to just kind of continue to reinforce that message. And so then I'm going to talk and kind of highlight two approaches that I implemented into my classes to really deploy this in the classroom, not just in kind of an extracurricular activity. So, and I'm going to talk about it from the standpoint of general research skills and then topical research as well. So, talking about motivation. There's a lot of literature out there on the benefits of undergraduate research. It gets students excited, it gets them interested. And they've shown with data, which I don't have a bunch of data today, but there is data out there that shows that if you get students involved in an undergraduate research program of any type, there's a higher likelihood of those students going into getting an advanced degree. It shows that students are more interested in actually staying in the discipline after they get their degree, where I think all employers, as Tara was pointing out, employers are desperate for our students, and if we can make sure that they actually stay in engineering, I think that's what we should be aiming for. And then the other thing that I've noticed, and I'm glad you all mentioned it too, is we get this extended time of mentoring. They may only want to stay and do a master's degree, but I've had several colleagues that it's very common for them to pick up a first-year engineering student, work with them for 4 years, turn them into a master's student, and actually one of my colleagues even has 2 PhDs out of a student she picked up as a freshman, which is pretty outstanding. So lots of really great opportunities, sounds all rosy, but there's obviously a lot of challenges with this too, and it comes from the students themselves. There may be a lack of maturity, there may be a lack of technical background. It's great to involve the first year students, but what background are they bringing to the table? Some physics knowledge, calculus, things like that. If I want them in the lab mixing concrete and helping with mixed design development, that's not a class they're going to take in my program for a couple of years. And to build on that, even when we start to talk about research methodology in general, and again, Tara pointed this out, data security and just taking careful measurements, this is a skill we don't necessarily emphasize or pick up in maybe the Gen Chem courses and the physics courses that they're taking prior to some of their upper level courses. And then again, to build off of that, a lot of our students are not coming with strong problem solving backgrounds. They're really good at solving very canned, closed form problems. If you instead give them a more open-ended problem and say, you have to think creatively, come up with some solutions, that's a big step for our undergraduates. So lots of challenges, and then we start to think about it, well, what's the difference between an undergraduate and a first-year master's student? And it's maybe a couple of months, maybe a couple of years. Well, they don't magically just get all of the skills necessary to be a successful master's student because they have an undergraduate degree. And so as I've talked to colleagues who have struggled with master's students, struggled with new PhD students, I said, well, let's maybe start to think about and address this. So, starting to rethink how I run some course projects. The advantage of running a course project, we can start to cast a wider net for our students. So, in the previous slide, I said, you know, there might be a maturity, a lack of technical background. Well, how do I know their maturity without having a bunch of experience with them and investing in those undergraduate students? Well, it is an investment. But if I have them in class doing a project, well, that's a much wider net. They're all going to do the project. I'm going to get a lot more experience with them because I'm going to give them a grade, so I'm assessing their work, and I get that firsthand experience. So that was the first thing as I'm rethinking my project. Okay, now I'm going to actually touch on certain skills, but I'm also going to see how a range of students react to it, not just the ones that raise their hand when I say, hey, who would like to do some undergraduate research? With this approach, I'm also now rethinking how I run the projects. It's not just go and design something. I'm rethinking, okay, so what skills are going to be really necessary for a new master's students? And this has come from conversations with a lot of my research colleagues. Where are the deficiencies you're seeing? And believe it or not, you know, they're identifying a lot of the same weaknesses. Things like, okay, designing an experiment, analyzing results. So when you get the results, get the numbers, getting the student to think of how do we present those beyond just, well, hey, this number is bigger than this number. Well, there's an opportunity to add some depth to how we look at that. And so the other thing we can do is start to develop interest in specific research areas. So, and I'm going to talk about what I call my topical research, but believe it or not, I don't have a ton of first-year students who say, I love concrete. I don't understand why, but they don't come in to civil engineering thinking, oh, I really want to do concrete mix design. No, they come in, they want to change the world, they want to save the environment, they want to build the tallest building. They have these kind of grandiose ideas, and so, you know, part of my job is I should get them excited about the concrete mix design. And so if they're in my class, I hope they walk away being a little bit more excited about potential research avenues related to what I taught. So, as I said, I kind of came up with these two research or two projects styles that I'm using in two different courses, and so I'm going to talk about both of them. And so the first one, I'm just going to call it general research skills. Again, this is based on conversations with colleagues that a lot of the general research skills are not there. So the one project addresses that, and then the second one has been feeding into my research, which is dealing with concrete mix design, and we're going to talk about both. So, with the first one, and again, I'm calling this general research. The idea is that I want the project to support the course objectives, but then also sneak in all the research skills that would be necessary in a graduate program. And so what are these skills that I keep alluding to? Well, experimental design, experimental design, experimental design. It is really interesting talking to students who, you know, maybe they've taken a materials lab, they've taken a couple chemistry labs, they've taken physics labs, and you ask them, okay, so test this variable. And then they come back to you and they've changed 8 variables 3 times, and they come and say, oh, well, it's clearly this other obscure variable. And there's not that, embedded knowledge in prior lab work that would help to get them to understand, okay, I take one variable and I start to vary it, and then we see how that effect plays out. And I think part of this is a lot of our labs are canned. They're prescribed. Go to this machine, stick the specimen in, press this button, tell me the number you get out of it. And so they don't actually have to think about what they're doing. They're just reporting values. And when we start to think about that in light of ABET student outcomes, where it's the one about designing experiments and designing and conducting experiments, how many of our students actually are designing experiments in their undergraduate curriculum? I think there's definitely room to improve there. So with this one also, the skills I'm talking about are instrumentation and measurements. And again, this comes back to Tara highlighted being careful in measurements. But then also understanding what tools are needed to get those measurements, tools that are probably pretty common to different types of graduate research, and I have some examples for that here in a moment. And then everybody's favorite thing to talk about is statistical analysis. All the undergraduate curriculums that I've been involved with, that I've looked at, they have a stats class. But then when you get to graduate school and you start to say, okay, well, are these two numbers statistically different? There's a loss, because there's not that connection of, oh, I can actually use this tool I learned and apply it over here. And so I said, okay, these are important skills. Let's package them all up together and see what a class project looks like. So that's what I did. The course that I teach this in, I actually kind of built the whole course around this motivation, but it's a measurements and instrumentation course. And we talk about experimental design, we talk about statistical analysis, and how do we get all of this stuff working together so you get good data that when your advisor asks, okay, are these numbers different? You can say, yes, they are statistically different. I have this confidence interval, and you actually understand what that means. Now, this is taken mostly by our upper level undergraduates. I've had like one junior, most of it's seniors, and then it's actually all of our rail graduate students take this course, oddly enough, because this course is actually really content agnostic, I like to call it, where it doesn't matter what area of civil engineering you're in, this is relevant to you. So what do I tell them to do for the project? I make it as hard on myself as possible. I tell them, go find something and measure it, and do a small research project on something you want to know. Okay, and so some of them try to tie it into their research. Some just, they ask a weird question about something in the building, and then they go and measure it. And it's very open-ended that way. So they have to develop a research question, develop a hypothesis, develop the experimental plan, how are they going to test their hypothesis, and then actually do the instrumentation design, data collection, data analysis, all the statistics. And then of course they write all of this up, because of course then we can build in some technical writing skills as well. So what do these projects look like? I just am highlighting two from the last time I taught it. one group of students came to me and they said, we want to understand the temperature fluctuation due to double doors or single doors in a building. And I said, okay, that sounds like that problem's been solved and maybe not be that interesting. And these were two geotechnical engineers, so I was really confused why they thought this was going to be really interesting. And what they found was, in fact, that double doors maintained indoor temperature better than single doors. Okay? Again, not surprising, not revolutionary. But what was interesting about their whole project was the level of thought that they put into how they collected data, the care they took in when to sample the data, the parameters that they needed to use to establish trends, and then coming back with a statistical analysis to actually support everything they saw and measured was actually really fantastic. And the Pareto chart there is, it's just ordering the effects of different variables. And so they looked at the delta T between the inside and outside temperature. They looked at the distance. And they found that, those were actually, one was statistically significant. The distance wasn't as significant. But the duration that the door was open was. And so, again, this is fully expected. This was part of their hypothesis, but they just proved it. And they were very careful in when they measured, how they measured, and they had a really nice plan put together. The group below, we have a relatively large printer that this is a large 3D printer that when it moves very quickly, and it can actually vibrate, which if you're familiar with printing, if your printer is shaking all over the place, your print does not turn out very well. And so I said, this is kind of a problem, and they said, we're going to try to understand this. And so this group looked at correlating vibrations, deflections, and stresses with certain movements of the printer. And so again, they chose the instruments, they collected the data, and then they put that all together into a nice cohesive story about, okay, when you do this with the printer, this is going to happen, and then we can actually take that back and improve our printer movements to avoid some of these vibrations. All right, so that's one example. The other example is, okay, so let's start talking about concrete. We're here at ACI. So with this one, I like to think of this as almost crowdsourcing some initial testing for research that I'm interested in. And so this is where I take the project objectives, and I want to make sure, of course, they are supporting the course outcomes, but then I have a specific research objective in mind, and I kind of stir them all together, make sure they're all working together cohesively. And so here I want the students to now start thinking about how to do a literature review, how to read scientific literature. I do experimental design, but to a lighter degree. And then we also talk about testing and data analysis. And now we really focus on problem solving because I'm going to give them a new problem. With the previous examples, the testing they've done, there's established precedent for what they did. With this, because it's more research focused and these are research questions that I have, well, there's not a well-established solution for this. So I had shown you the larger printer, 3D printer that I have. This is our small 3D printer, and this is for concrete. I teach a concrete materials course. Once again, this is the upper level undergraduates, as well as a a lot of first-year graduate students that'll take this course. And so what I challenge them to do is develop a new standard test to assess the workability of printed materials. And again, where I'm hoping to fill in a knowledge gap here, there are no established, this is the test for printed concrete. It's not like slump where that's the workability test and for conventional concrete, and that's that. Okay, we don't have that for 3D printed concrete. And so I want them to kind of crowdsource some ideas of how we could assess this and actually get some new ideas going. And then the other one is just developing mixture design. We have to have very targeted properties with our mortar in this case for it to be able to extrude and then support itself. That takes a lot of work and a lot of just trial and error and trying to figure out how to make this all work. So in this one, the students develop a literature review. So there's a lot of literature coming out every day about, okay, here's a mix that worked, here's some behavior that worked, here's some tests that we came up with. And so they're gonna use some of that knowledge to start to build their particular project deliverables. They have to come up with an experimental design. So thinking about, okay, I need to look at this variable, and then I'm going to look at this variable, and I emphasize very clearly it's simple factorial experiment. So you vary one variable at a time so we can get kind of clear behavior to variable interactions here. And then they have to iterate the design, so they have to do some trial and error with it as well. And again, this is kind of intended to not just do some preliminary problem solving for me, but then I actually am going to recruit out of this project based on interest that's generated. And so on the mixture development, you can see that early trials are not always successful. But usually by the end of the project, they've kind of gone through this iteration. They've worked through an experimental design, and they end up with a relatively high quality result, which is, you know, this one down here in the middle is nice, clean, very distinct in what they did. And then with the workability testing, they come up with all sorts of crazy ideas. I've had students use plastic baggies and try to like pipe the mortar like frosting. Here's like a funnel and plunger method. I don't know what's going to work and eventually be the standard test for 3D printed concrete, but I've gotten some ideas for tests based on some of these ideas they've come up with. And so interesting results, and again, they have to write all this up, and I save this for my own ideas. So one success story that I'm going to talk about then is this is my student Benjamin. He went through the class, got really interested in it, said, hey, I'd like to maybe get involved in some graduate work. And he came in at a time when we had a contractor who has one of the large Cobod printers, and he wants to start printing houses. And he said, hey, I need some help with mixture development. Ben was able to actually step right in alongside the contractor and start helping them with the mixture development. And instead of taking a semester to get up to speed on the literature, get some lab experience, and then start helping, he actually used a lot of what he learned in the class project to kind of get himself rolling, and within a month or two, he was contributing effectively to this larger project right away. So, and he even is the two pictures there on the right are some tests that he was kind of playing with in his class project, but then he was actually deploying with the contractor's help to again, rethink what we know about workability. So, all right, in summary, these different approaches have yielded positive results. I don't have data other than anecdotal stuff. The student that's working with me, I've had several faculty come and tell me, thank you so much for teaching this stuff. I'm going to make all my students take it. Like I said, this rail group, they send me every single graduate student now every time I offer the class. It really is an effective way to start to build in real research skills and start to kind of identify students who maybe they didn't really consider graduate research. It was an option for them. And they find that, oh, this was actually a lot of fun. They really liked the research or the topic. In the future, I'm going to continue to expand this kind of framework. I'm talking to some of the other faculty who teach labs in other disciplines to see if we can kind of replicate that. And then we'll start to really look at data collection and in regards to the student outcomes, hopefully be able to track some students and see how many we can actually convert into researchers. And with that, I will take questions. So with that one, even though I do have a mix, that one was actually, I did collaborate a little bit with a colleague who teaches that to undergraduates only. They had made an instrumentation and measurements course to address the ABET outcomes. The course I teach is 100% accessible to undergraduates. The only reason I think I only get seniors is because of just curriculum scheduling, we'll call it, that they can't really fit it in until later in the degree program. So, yep.
I'm curious about the same project. Do students apply like their own instrumentation? Do you purchase that as part of like a lab fee, or how does that?
So yeah, so some of it is kind of a lab fee type of issue. I have been very fortunate to get some equipment grants to buy a bunch of the equipment to support the class. And then I was also given from a faculty who retired. He had basically accrued a bunch of, it's actually Pasco measurement devices that he got through, I think, an NSF grant many years ago. And so he gave them all to me when he retired, and so now I give them all back to the students, and so they're using it in this measurements class. So.